Okay, off we go. So, last time we were talking about partial derivatives, and we spent a little bit of time defining, how do you compute partial derivatives, and we spent some time interpreting what do partial derivatives look like. I'm going to remind you of really the big point there. The big point is that you're going to get different geometric interpretations depending on what kind of pictures are you looking at, right? This ever-present problem in multivariable calculus that sometimes you're looking at a graph, in which case partial derivatives will be interpreted one way. But sometimes you're not looking at a graph. Sometimes you're looking at some other kind of construction, and partial derivatives are interpreted totally differently in those different kinds of pictures. So, for example, this literal picture, I'm just going to hit this point again real quick. The partial derivative, here it's not a slope. Here it's a factor, right? It's not something that actually geometrically shows up in the picture itself. It's a relationship between the input change dy and the output change df. Okay. All right, so we talked about that last time. Let's see here. Okay, how do we interpret it in terms of level sets? Now, again, a different kind of a picture. And this one's a little bit dangerous, actually, because at a quick glance, you look at a particular level set of a function, and a level set, a single level set, it's a curve. And you're going to have this temptation in your mind to think of, it's a curve, and we're talking about a derivative, and the derivative is the slope of the curve, right? Because that's been drilled into you since you were, however old when you took calculus, right? So you have to resist that temptation, because that is not true. Derivatives are not slopes, except in the special case where you're looking at a graph. Right? And these are level sets, not graphs. So you cannot take that interpretation. So this is another one of these situations where the partial derivative is not actually itself geometrically going to be like something you can point to, there it is, right? As it is with graphs. It's something you can kind of infer from the picture. So let's look at these level sets right here. We've got various level sets. I'll use green. How about kind of highlight? Anyway, not my best tracing. But there's a bunch of level sets, various different level sets. And for making these interpretations, I find my favorite point of view on this kind of thing is to think about these as being contour lines on a topographical map. Right? So pretend you're out hiking, and this is what the topographical map looks like, and the two different directions that you might go, right, when we're talking partial derivatives. On the one hand, you might talk about moving in the x direction. Partial of f with respect to x says how fast is the function changing as I move in the x direction. Well, I can just start imagining that I'm there and that I start hiking in that direction. And look at this, it's almost like I'm going straight uphill, right? I'm crossing contour lines fast as I go in that direction. That seems like it would be steep. The graph of this function, therefore, I would interpret as it would probably be steep, right? And so I'm going to infer that the x partial is large. Now, by contrast, on the other hand, let's suppose that you were going in the y direction, and keep in mind, that's what a y partial is. The y partial says, suppose you're moving in the y direction, exactly. Well, again, look at the contour lines. Imagine that this is your hiking plan, and if you're at this point and you start going in the y direction, well, it takes you a lot more distance to cross those contour lines. That seems like a much more pleasant stroll. As opposed to, climb, right, in the x direction. So I would imagine that the mountain's not that steep in that direction, or said differently, the graph is not that steep, or said differently, the function's not changing very much as I move in that direction. Said differently, the partial derivative I would expect to be small. So again, now, can I point on this picture to where is the partial derivative with respect to x on the picture? Now, not really. But again, you can kind of infer it. Okay. All right, so again, I emphasize, note how different this geometric interpretation of partials is from this, in this literal picture context, and certainly from this in the graph context. Okay, same partial derivatives, totally different geometric interpretations. Okay. All right, so let's see here. Yeah, moving along. So we're going to talk about something called linear approximations, and quick apology, awkwardly, linear approximations are not linear. It's a little silly, but I'm going to explain in a bit why they're called linear approximations. There's actually a reasonably good point there. Side note, there's something called affine. Y'all don't need to worry about that. So I'm going to start by saying, let's assume that a linear approximation exists. You'd be surprised how subtle that question is. I am going to wave my hands at this question in a bit. But it's actually some quite deep water that we're going to mostly just kind of sail right over. I'm going to point to some things and try to, make a bit of a case for why this is, how mathematicians deal with this surprisingly deep question. But for the most part, we're just going to assume linear approximations exist, and then I'm going to show you a really handy little computational quickie that will allow you to establish with full mathematical rigor that a linear approximation exists. Anyway, we'll get to that. So that said, okay, the linear approximation, let's just think about single variable calculus. Y'all remember this formula right here? There it is. That's your linear approximation. And what makes this the linear approximation is a subject of some discussion, I suppose. Different ways to think about it. There's a particular point of view I think is the most useful, and that is this is the unique degree 1 polynomial. There's only one at most. We're assuming it exists. So there is exactly one degree 1 polynomial that has the following two features. It has the same value as f at the given point, and it has the same first derivative as f at the given point. So this is the unique degree 1 polynomial. Let's say this geometrically. If we were looking at graphs, the graph of this is the unique line, right? That's kind of geometrically how you're going to think about it. That has that mimics the function f in terms of value and derivative, in terms of what it is and where it's going, right? So on a fundamental level, this is a pretty natural thing to want to talk about. This is the best possible mimic of f in these senses at the given point A that we're interested in. Okay, now I'm going to wave my hands quickly at check and make sure that you understand why that's true. Confirm these two properties. Take this formula right here. Confirm that these two properties hold. Now you're going to have to think about, well, how would you go about doing that? The first one's pretty easy. You take the value x equals a, right, and you plug that in right here, and boom, it just works. That part's no problem. The second one does require a little bit of a subtlety, a little micro subtlety, and that is you've got to take the derivative of L. You got to take this expression, take the derivative. You got to do that before you plug in x equals a. Right? So x is still a variable. You take that derivative. You got to remember that this thing right here is a constant. After all, that does not say f prime of x. Very importantly, this is f prime of a. So as you take the derivative to compute L prime and your attempts to check number 2 here, this is a constant, and you treat it as a constant because it's literally a constant. And so keep that in mind as well. Now, if you keep all that in mind and you go through and just brute force confirm, this works, and that's why we like to call this the linear approximation. Okay, so here is the multivariable real valued but multivariable version of that same thing. So just to be clear, notice now several input variables. So this is a multivariable function. Again, real valued for the moment. We'll get to vector valued in a few. Again, I'm just going to write down the formula and leave it to y'all to confirm that this works. And this is a straightforward, take a deep breath and plow confirmation. I claim this function does it. I claim this function has the analogous properties. This has the same value as f at a given fixed base point A. And this has analogous, again, to what we did in single variable, the same, I've got to be a little careful with my terminology here. Up here I said the same derivative, by which I meant the only derivative there was, right? But now we have to acknowledge, okay, there's actually several different kinds of derivatives. We've talked about various different partial derivatives. So my claim is that all of these partial derivatives, first partials, we'll talk about higher partials later, all of these first partials, L agrees with F on all of those partials as well. So totally analogous to what we did in the single variable case. And again, this is a matter of just direct confirmation. Now this, again, healthy exercise, and I hope you all will take the time to crank out and work it out and make sure that you see how this in fact works. Right? This totally works in the sense of it satisfies these properties. So make sure you can do that. Analogous things to keep in mind and easy to get confused on. Don't forget this thing right here. That's a constant. And it doesn't exactly look like a constant. You see a function f, and it says take the partial of the function. It's going to give you another function, right? And so shouldn't that be a function, right? How is that a constant? And just keep in mind this bar here, this vertical bar with a little subscript with a point. That's just a notation, sort of an alternate notation that says, yeah, take this function and evaluate it at that point. It's sort of an alternative notation for. Let's see here. Let me. This notation is kind of an alternative to, parentheses as a way of indicating you're plugging a point into a function. So that, in fact, is a constant. Yes.
So all the partials are constants, just not.
All the partials that are in this expression here are being evaluated at A, and therefore are treated as constants. That's right. Exactly. Yep.
Can you explain again why the x minus a is there?
Well, so that's for you to crank out, right? It's there because it works. Yeah, it's there because it works. It's, that's just the fundamental reality of it. Yeah, and if you change that formula meaningfully, then it won't work. So that's why it's there. Yeah. Yes.
In this case, is a just like a vector, and then a
Yep.
is like the first coordinate?
Yeah, so A is a point, and then A1, A2 through AN are the coordinates of that point. Yeah, right. Yes.
Wait, I'm confused. This isn't like a polynomial breakdown. It's just the first one, and then its derivatives, but they're all partial. They're not continuing down.
I don't understand. I'm sorry.
Like it's not like a second derivative. It's just these are all first derivatives, but
Yeah.
okay.
Yeah. These are all. Yeah, that's right.
The
So.
end's not like another order.
So this says partial derivative. This says evaluate at the point A.
Okay.
Yeah. Is that cool? Does that make sense?
Yeah.
Yeah. Okay. Yeah. Okay. So now here's the problem. Having written this down, you notice it goes most of the way across the page. That's annoying, right? So there is a convenient observation that we can make about these terms. Now, again, that's not the entire right-hand side of the equation, but notice, if you would, that what we have is a bunch of factors in these various terms that all look pretty similar to each other, and those factors are being multiplied by these other factors that all kind of look similar to each other, and then we're adding we're adding a bunch of terms, each of which is a product of two factors. Where have we seen this construction previously? And you know what? In fact, that's a dot product. That is straight up exactly, computationally anyway, that's how you define a dot product. Oh, you know what? Let me zoom a little bit. If the thing will cooperate. Here we go. Yeah. Oh, and I forgot to do there we go. Oh, that helps. Okay, so let me try that again. So that is conveniently rewritten as a dot product. Now, the blue parts here are pretty easy to persuade that those are just the coordinates of the vector x minus a. And you think about the vector x minus a, the vector x and the vector a, and if you subtract, you just subtract the coordinates, and bam, those are the coordinates of x minus a. Likewise now, these green things, these are the coordinates of something else, and we haven't talked about this construction before. And for the moment, I'm going to present this as just being a notational convenience. I really dig the idea of being able to take this big expression and rewrite it compactly like that. That's really nice. In order to do that, I need to be able to give a name to the vector whose coordinates are these green factors here. So I'm just going to say, look, this if you have a bunch of partial derivatives, as I do, and you want to make a vector whose coordinates are these various, in order, the partial derivatives of whatever function you're talking about, we're going to use this notation. It's a weird little symbol, little upside down triangle. By the way, very important that it's this way, you can't flip it back right side up. The point's got to point down, not up. It means something totally different if the little point points up. So please do be super careful about that. We're going to call this the gradient for no particular reason that's evident right this second, but will be soon. With that in mind, what we have there is, all these green factors. That's just literally the gradient, the coordinates of the gradient of f evaluated at the point A. So, like that. So, for the moment, this is going to be our motivation for defining the gradient, what we're calling the gradient here. It's a notational convenience. This definition just allows me to rewrite this big thing as this little thing. Or more to the point, how you look at it. It allows me to write something written in, complex terms. I can rewrite it in terms of a meaningful construction about which I know theorems. Right? Dot products. We know a lot of stuff about dot products. Right? This is geometrically natural. And rewriting it like that is going to allow us access to using those powerful geometric theorems. So it's not just a matter of compactifying, it's also recognizing something that we have tools to deal with. Okay. All right, the example I've got down here is very plug and chug, so I'm going to be super quick with this. If you want to write the linear approximation of this function at that point, all right, well, here's the formula for the linear approximation. And just one bit at a time, I need to compute these. I need to compute f of a. All right, so I need to take my point, colors. I need to take my point A. I need to plug it into my function f. And what comes out is that. Plug and chug, y'all can do that. Next, I need to compute the gradient. Okay, well, let's see here. The gradient. The gradient's made up of a bunch of partial derivatives. So we take the appropriate partials, right? Partial derivatives of the function f. So there you go. We do need to plug in, again, the point A. So here's the point A. I'm going to plug this point A into these expressions. And then I get that gradient is missed. this, which goes there. I was just plugging in, yes.
Why is the partial derivative with respect to x not 2x plus y squared?
Because when you take a partial derivative, all the other variables are treated as constants. And the derivative of an additive constant is 0. Does that make sense? It's an easy mistake to make. So you really got to think, you got to impose aggressively in your mind that you know exactly what the process is. A lot of students make that same mistake. Okay. All right. So, just plug and chug. And, of course, x minus a, don't forget that a is that given point. And there you go. Now there's this sort of optional question of do I take this expression that I just computed and should I sort of multiply it all out? It depends on the situation, I guess. It depends what your purpose is. Frankly, for most purposes in a class like this, I don't really see what the point is. Right? What do we all gain from rewriting this as this? Bit more compact, I suppose, but I like what we have here because I can see the value of the function, the evaluation of the gradient, the fact that I'm doing a dot product, the fact that this is x minus a. There's a lot of information visible, discernible from leaving it written like this. And when you multiply it all out, what you get is this opaque, uninterpretable, yes, slightly more compact expression, but so what? It doesn't really buy you that much. If you're going to sit down at a computer and code, and you're going to need your computer to crank out several trillion of these computations using exactly that formula, oh, for God's sakes, yes, do this one, not that one. Yeah, absolutely, of course you would. But we're just not going to be interested in that most of the time. So most of the time, I'm going to encourage you to leave it like this, unless the question explicitly says otherwise. Okay. Now, reminder, all of this was for real valued, multivariable, but real valued functions. So now we're going to entertain what happens when we go when we go vector valued. Now, real quick, I want to point out, and if you look at our single variable formula, and now you look at our real valued multivariable formula, and you compare these two formulas, golly, they look a lot alike, don't they? How about that? F of A, F of A. Something times x minus a, something dot x minus a. The something up here is a derivative. The something down here is a bunch of derivatives. It's not exactly the same, right? But there, you can see a pretty strong analogy there. So we would kind of expect something vaguely analogous, perhaps, to work for the vector valued case, and it does. Now I'm going to show this to you in a slightly different way. I'm not going to write down all the cranked out terms and then compactify it with cleverly chosen notation after. I'm just going to start with the cleverly chosen notation because otherwise it's too bulky. And here it is, the convenient notation. When you have a vector valued multivariable function and you want to write down a linear approximation, we're going to need this monstrosity here. And for the moment, I'm gonna call this df. It has another name. It has another interpretation. I'm going to try to restrain myself from saying the other name because I want to be able to build up the ideas that justify that name that I'm going to do my best to avoid saying, just for dramatic purposes, I guess. But anyway, for the moment, I'm just going to call this df. And in the same, analogous to how gradients are vectors made up of partial derivatives, this is a matrix that's made up of partial derivatives. Now, those partial derivatives have to be put into the matrix in a highly structured way. You're going to notice quickly that all of the first, wrong color. All of the first column are partials with respect to x1, et cetera, et cetera. All of the last column are partials with respect to xn. So it's reasonable to refer to these columns by for each one, the common characteristic of all of its elements. So I like to refer to the first column as the x1 column, because they're all partials with respect to x1. Right? So something to think about. The big point here, make sure to remember, columns correspond to input variables. These are input variables x1 through xn. Okay, then you also notice, and it just has to be pointed out, that the rows, let's look at that first row, every entry in this row is a partial of the first output coordinate, f1. Et cetera, et cetera. The entire last column, the mth column, every entry is a partial of the mth output variable. So again, pretty common terminology. You talk about the various different rows, and I think it would be pretty reasonable to refer to this first row as the F1 row. Again, the shared characteristic. So columns correspond to input variables, rows correspond to output variables. You've got to keep that straight. If you get it backwards, you're going to transpose your DF matrix, and it's just a catastrophic failure of this will not do what it's supposed to do if you write it down transposed. So easy mistake to make, terrible consequences if you do. Please be very, very careful with that. Okay. With that notation settled, here's the formula for the linear approximation. And notice it's got that same structure, right, that the previous formulas had. It's f of a plus something times x minus a. It's just that now this something, it's not a scalar that you're multiplying by x minus a. It's not a vector that you're dotting with x minus a. It's a matrix that you're matrix vector multiplying by x minus a. So structurally, very, very similar. Detailed devils, significantly different. And an exercise, again, that I'm going to leave to y'all. And by the way, don't do this in full generality. It gets too unwieldy. But I suggest that you take a function from, let's say R3 to R2. Right? Don't go crazy. And write down the entire DF matrix that you would put here. Write down, expand out this expression, and then confirm that not only does it have the same value as f at the point A, but also all of the partials of all of the output variables with respect to all of the input variables. L agrees with f in all of those senses as well. So if you do this as for a function from R3 to R2, you'll have 6 partial derivatives to check. It's not that bad. Be organized about how you write down your terms, and it's just a matter of doing it. Again, nice exercise. I hope you'll do it. Easy example that we're going to blow through pretty quickly. Excuse me. How are we going to find the linear approximation of a given function? Well, I'm just, again, going to plug straight into the formula. You compute the value of the function. Now, this is a vector-valued function, so that value is, of course, a vector. That's the name. Let's see, now the kind of detailed part, you've got to compute the derivative matrix, and the derivative matrix is a bunch of partials. You've got to plug in the point A that's given. That's got to plug into there, thus giving you then the evaluated derivative matrix here. That goes there. Partial derivatives, plugging in numbers, no tricky curves. Okay? And then, of course, you're multiplying that matrix times x minus a, just like before. Okay, so boom. Everybody all right? All right. Okay, couple of quick observations here. These are super quick. we've already kind of made this observation that the columns correspond to taking partials with respect to specific input variables. Right? So the first column is the x1 partial. Here I'm just making the slightly different observation. So not a deep point. Don't worry about this, but slightly different observation. If I were to take f itself, f, not its coordinates, if I were to take f itself, a vector valued function, and take its partial with respect to x1, hopefully no surprise, what you get is the x1 partials of all of the components. And you can confirm that for yourself. You just write it down, and of course it works. So slightly different observation here. The columns are literally the various partials of the vector valued function you started with. What is not immediately obvious, but which you'll notice, is that the rows are gradients of the coordinate functions. So let's come back up here to our thing here. And, I initially called this just, all of the partials of f1. If you think about it, f1 is real valued. f1, the coordinate function, f1, real valued function. These are all of the partials of that real valued function. That is the very definition of gradient that we wrote down right up here. Right? So the rows are gradients. It's a neat little fact. This DF matrix, this thing that we're going to talk about so much in this chapter of the course, the columns are partials, the rows are gradients. Okay. Okay, so back to something I alluded to previously. Why do we call these linear transformations? And the point is, you see the matrix. The matrix is doing most of the heavy lifting in the formula. This matrix, here, other than this matrix, it's just, you multiply and you add. I mean, that's the magic trick. DF is the thing that makes this work, right? And that by itself, if you ignore what else is going on in the function, being a matrix, it's linear. So even though L is not linear, DF is. All right, another little quickie observation before we get to some harder ideas. Let me flash back to Calc 1. Y'all remember tangent lines? And there's all sorts of little sloppinesses of terminology that they allow people to get away with in single variable calculus classes, and I've harangued y'all enough about functions are not the same as graphs. If graphs are just one picture, just replay that in your mind. So along those lines, tangent line is not the same thing as a linear approximation. A linear approximation, missed. A linear approximation is a function. Linear approximation is an algebraic object. It's a function. It's not a picture, it's not a geometric thing, it's an algebraic object. The tangent line is what you get when you set that function equal to a new variable y, namely when you say, I want to talk about the graph of that linear approximation. That is a geometric object. It is the arbitrary geometric visualization tool called the graph that relates to the linear approximation. But again, very importantly, not the same thing. So please do try to keep these distinct in your minds. Nevertheless, tangent lines and linear approximations are, of course, very, very closely related. They're so closely related that, again, in Calc 1 classes, they pretty much call them the same thing. I mean, I've seen this called the tangent line many times, and it's just a little nails on the chalkboard for me. But what are you going to do? So, moving along, we can do the same thing for a function of two variables. Totally analogous. we can take a function of two variables. Now, you notice I'm drawing graphs, right? So I've got input variables here, x and y, and output variable z, right? So we're looking at the graph picture. And with that noted, this is the linear approximation. We wrote that down a few pages back. It's a function. It's an algebraic object. It's not geometric. It's just a formula. It's a function. But we can talk about its graph. Again, setting the values of that function equal to a new variable. Now we're talking about the graph of that linear approximation. That is a geometric thing, and that's what we call the tangent plane. Analogous to the term tangent line. Everybody good? Okay. Right. And by the way, I mean, you look geometrically, and it does kind of the same job. I mean, this tangent line here is kind of tracking geometrically what the function's graph is doing at that point, right? So tangency, it's it's the extended sort of, if you look at the small scale and see what it's doing and just kind of extend that out linearly, then you get that tangent line. So likewise down here, the tangent plane, we call it that because the tangent plane is literally what you get when you look at the very small scale of your graph, right? And kind of see in what direction is the graph kind of pointing. If you just keep extending that in a linear fashion, you get this thing, the tangent plane, namely the graph of the linear approximation. Okay. All right. Okay, now on to some much more interesting stuff that I'm sad to say we don't have time to talk. Oh yeah, question. Okay.
The tangent plane, is tangent across one line or one point?
The what now?
The tangent plane, because a tangent line only touches the graph at one point.
Yeah. But the tangent line touches the graph at one point as well. Yeah, and so the tangent plane, likewise, typically, generically, the way I've got it drawn there anyway, it touches the graph at just sort of the one point.
So it's not across a line, or is it?
It's not a what now?
I thought it would be it crosses the Z plane on one line. Or it has a contact point.
Crosses. I mean, so look, we've got a surface.
Yeah.
There's a tangent plane.
Okay.
And you see how it's only touching my knuckle there at just that one point? That's what it is. Does that make sense?
Yeah.
Okay. Yeah. Cool. Yeah. Okay. All right. Okay. Again, one of the things that makes me sad, we can't talk about this really important idea, if you think about it, right? We're doing multivariable calculus. One of the big ideas of calculus is derivatives. Whether or not it is possible to compute a derivative in a way that's usefully meaningful, kind of a big deal, one would think, right? And yet, it's sadly just not quite what this course is about, right? I'm going to say this is an abstract discussion about how to avoid anomalous problems that are very serious in sort of, math contexts, but in most engineering type contexts, not that big a deal. It's not really, it's easily avoidable in other ways, and ultimately just not really what this course is about. So we are going to blow most of this off. I am going to show you the very broad strokes of differentiability, but don't. I don't want to. It's not that you don't need to know this. It's that you don't need to sweat this. This is just for helping you have a picture in your mind, and I do want y'all to have the right pictures in your mind. But this is not something that computationally you're going to have to worry about. So we're going to return back to the question that I previously noted. How do I know there is? How do I know that a linear approximation exists in a meaningful sense? What should it mean for something to be a linear approximation? I can write down a formula, but how do I know that formula is not garbage? Do I really like this formula I've written down? And if so, under what circumstances? So just to show you that this is something to worry about, let's look at this function down here. It's a weird function, I'll give you that, but this function is 0 in most places. Off of the x and y axis anyway, this function is going to be 0. So the value of the function is 0 in most of the xy plane. But if you're on an axis, right, if either one of your coordinates is 0, on the axis the value of the function is 1. So again, on these axes, the value of the function, like this, it pushes up like that, and the value of the function is 1. So we're going to have that and this kind of like the little marionette, the little, I don't know if y'all know what I'm talking about, when you have the little doll that they make dance with the strings, right? So there's this little kind of cross-shaped picture that's elevated up where the function is 1, and then everywhere else the function is 0. Weird function. Granted. But let's look at our formula and see what we think about our formula in the context of this function. Can I compute the value of this function at the origin? So we're going to look at the origin here. So that's 0. That's 0. Looking at the origin. Well, the value of the function is clearly 1. And can I take the partial derivatives? Yeah, sure. No problem. The partial derivatives just say wherever you are, start moving. For example, let's talk about the y partial. Start moving in the y direction, and the value of the function does not change at all as I move in the y direction. It's constant in the y direction at that point. And so, the partial derivatives are just 0. So this is the picture of why the y partial is 0, and likewise the x partial is 0. So, looking at the algebra, how this seems to be working out, you take all this information, you plug into our formula for the linear approximation. There's my, quote, linear approximation. This is what my formula gives me. And yet I claim that stinks. I claim that's horrible. That says that I should approximate this function by, just 1 everywhere. That's somehow a good approximation in a meaningful sense. And look how bad this is. It's hilarious. If I approach the origin, let's say through the xy plane, kind of coming at it from some angle like that, well, the value of the function, that whole way, the value of the function is 0. It's all zeros. That's what the actual function is, all zeros. But what would like to call itself my linear approximation is always 1 as I do that. Is a whole bunch of 1s, is that a good approximation of a whole bunch of zeros? No. Ridiculous. Clear garbage, failure. That formula we wrote down a couple pages back does not work here. Does that make sense to everybody? This should be unsettling, right? Because, we thought we played through, y'all are going to go through and start taking partials and confirm that this is supposed to have all the right properties. How is it not doing exactly what it's supposed to? And the answer is, I assumed unfairly that the linear approximation exists. That just wasn't true. This is a great example of that. So here's where I'm going to start moving quickly through this. There's a temptation to say, okay, look, the problem is that I was getting wrong answers. How wrong I am is called error. Error is the difference between the value that I should have and the value that I am approximating it with. And shouldn't it be good enough to just say let the error approach 0? And I want to dispel this tempting nonsense first. And let me just show you why it's ridiculous to claim that when the error approaches 0, we have to call that a good linear approximation. Let's take this function right here, f of x equals 5x. Right? And then suppose someone comes to you and says, I think 3x is a good linear approximation of 5x. Now, when you stop laughing at them, right, you would point out that not only is this picture bad, right, but this is the rejection of this idea that error points out how bad the picture is. Here's my error. My error is approaching 0. Right? So, are we persuaded by the fact that the error is approaching 0, which it is? Are we persuaded by that this green graph is representative of a good linear approximation of this blue graph? No, nonsense. It's not even going the right direction. Right? So this idea that error is the distinction is it just doesn't work. So we're going to define this different related thing I'm going to call relative error. And it's defined by this formula right here. You can see error is part of the formula for relative error, but we've got a denominator. So it's not just how far off are the output values. It's that divided by how far away are the input values. And this ends up making a great difference. So error is nonsense, but relative error does the job. So again, our same silly example. There's a function of which I might want to do an approximation. Here's a terrible, ridiculous, hilariously bad estimate. 3x, trying to approximate 5x. Clearly not what we want. Will our new test reject this obvious nonsense? Well, the relative error says we're going to take the error and divide by how far off we are in the input. And if you take that expression and crank it out, etc., you get 2. You don't get 0. So relative error in this case does not go away. Relative error does not vanish. Relative error does not approach 0. That is the rejection of this green curve, as of course it should be rejected, right? But this is the algebraic way of saying that's why I don't like this curve. That's why this should not be considered. This should not be tolerated as a good linear approximation. Okay. So when you look at this definition down here, and this is yikes, right? Or doesn't that look scary? I found this super scary when I first saw it. All this says is that relative error approaches 0. That's it. That's all this says. And so let's walk through and see that. Relative error approaches 0 as x approaches a. Well, relative error is defined as error divided by x minus a. Don't forget error is real value minus approximated value. Don't forget that our approximated value, our linear approximation, right, is this formula here where I've distributed the minus sign. Okay? So this great big expression over here, this whole thing, it's literally just a sort of a fleshed out, rewrite of the idea of relative error. And so when I say that I want this great big fraction to approach 0, and that will define what we call differentiability. That's what will define what we mean when we say that this is a good linear approximation. All it's saying is I want to avoid nonsense like this. Okay. All right. Now one last little bit of terminology, and we'll call it a week. And that is, if you look up at this expression, Yeah, you can think of this as the real value minus the approximated value, the minus sign distributed. Sure. But notice, look, I can just kind of group these terms a little bit differently. Let's look at this minus this. Now, I didn't do anything there, right? I'm just viewing this expression in a slightly different way. And these things down here, these have different nice interpretations. This is what we call colors. This is what we call the increment. This says, starting at a point A, moving to a point X, how much does the function actually change? Increment means the actual change in the actual value of the actual function. This other thing over here, this is what we call the differential. A differential, and I hope you all remember this from Calc 1 or 2, single variable calculus. The word differential just means a linear estimate of how much something changed. So the increment is the actual change. The differential is our linear estimate of change. So important terminology, increment and differential, and we will pick up there next time. Y'all have a good rest of your Friday. Try to stay dry. See you later.